Hey everybody. So we are now moving on to describing two variable data. So in this section, we will specifically be talking about um, two categorical variables. But before we do this, let's talk about what types of graphs and statistics we will use for every possible combination. So when we describe two variable data, it's similar to describing one variable data, but we're now looking at a relationship between two variables. So we identify the type of data we have, and based on what combination below in the table we have, we'll determine which numerical summaries we use and which graphs we choose. So for two categorical variables, the graphs that we can use are clustered bar graph, the stacked bar graph, or a mosaic plot. If one of our variables is categorical but the other is numerical, we do a separate plot for every single category we have, and then we do a numerical graph. So the numerical graphs that we had were histograms and box plots. So what we can do is a side-by-side box plot, also known as a stacked box plot. So you can call it a side-by-side box plot or a stacked box plot. And I'm going to say plots because there will be multiple plots on this legend or this axis. Then we could also use layered or colored histograms. I don't particularly like those. Layered or colored histograms. So what happens here is we stack histograms on top of each other, but they have to be different transparencies and different colors, and it makes them very difficult to see. Let me change colors here. When we make these graphs, whether it's the histogram or the box plot, there's one graph for each category. So there's one graph for each category we have with our categorical variable, and they're all on the same axis. So that's important. They're all on the same graph, the same axis. And then for two for two numerical variables, the graph that we'll use is a scatter plot. And there are other graphs that some fields will use. We're just not going to look at them in this class. So now, when we talk about numerical summaries of data like this, the numerical summaries that we use are going to be exactly the same numerical summaries we would have used with one variable data. When you have categorical variable only, you use proportions. When you have one categorical variable and a numerical variable, you do the mean, the median, or standard deviation, IQR, or five-number summary for each of your categories. And then you may do it for overall as well. And then for two numerical variables, we can do things like mean or median for each of the variables, but we may also do some additional numerical summaries that you haven't learned yet that you will learn later in this module, and then more of them you will learn later in the semester. So let's do our first example with two categorical variables. So some examples of two categorical variables would be biological sex and what year you are in school, tree species and what season it is, biological sex and whether you're an adult or not. And when we organize this data, we want to order and summarize this data numerically using a contingency table. So you guys, this is our equivalent of a frequency table, but because we have two variables, this is called a two-way frequency table or a contingency table. The frequencies or counts of each category, or the relative frequencies or proportions for each category, are listed in this table. The table may or may not include the marginal totals, which are the totals of the rows or the columns or both. It may include marginal proportions, which are the total proportions of each of the rows or columns. And then once we make a frequency table, which here it's going to be called a two-way table or a contingency table, then we display the data using either our clustered bar graph, our mosaic plot, or our stacked bar graph. And we can calculate numerical summaries or statistics. We typically just use proportions or relative frequencies or raw counts for categorical data. Um, we may also calculate something called relative risk or odds ratios for categorical data. This is specifically used in the health sciences. So we will talk about that in this module and in this class. All right, so let's do our first example. Determine if there's an association between sex and if people smoke or not. The two categorical variables would each have two levels for this example. We have males and females, and people smoke or they do not smoke. Our explanatory variable here is their biological sex, and the response variable is whether they smoke or not. And the data can be found in the smoking Excel file, you guys. And then there's an R file that you're going to want to use that you can find on Canvas also. And I think it's called graph to categorical variables smoking.r. What you're looking for is the one that says two categorical variables, and that'll be the right R file that you'll fill in as you watch the R coding. So we can organize or display the results of these questions in a two-way table. So we would ask each person, is your biological sex male or female? Do you smoke? Yes or no? And those are the only answers we're allowing here in this particular study. We'll talk about differences to those answers in a few minutes. So this thing here is called a contingency table, or a two-way table, because it has two variables on it. And I have put sex on the rows and smoking on the columns, but you guys, it's completely fine to flip-flop those two things. And then I've also included the totals for the columns and the totals for the rows, but those are not mandatory. And in fact, the only part of the graph that you have to have are whether someone smokes or not, yes or no, and then their sex is male or female, and then the four numbers in gray. And so 15, 50, 10, and 65. Everything else is extraneous and not required, but it can be really nice if you're trying to do math on this information. So if we want to make this table in R, the code that we will use, we have to name the table. I'm going to call it smoking table. So smoking underscore table. So just like we did with our with our frequency table with one variable, we have to name this new table because it's a variable that's saved in our environment. And then you can either use an equal or a pointer. And then the command is still the same thing as it was for frequency table, you guys. It's just table. But instead of having the data frame $ variable, this time we have data frame $ variable twice because there are two variables. So our Excel file is going to be smoking. So I'm going to have smoking $, and it does not matter what variable you put first here. Our variable is smoke, and you can look at the Excel file to see that. And then you put a comma, and then the name of the data frame, again, smoking does not look like smoking, SMOKING, dollar sign, and the variable that's missing is sex. And this would get you a frequency table that we have down here, which we call contingency table. Now, this code might flip-flop our rows and columns, but we don't particularly care about that. If you're not happy, you can always flip-flop these two variables. Can flip the variables. And that'll flip which variables on your row or your column. All right, so the graphs that we would use to display this particular data, a contingency table, and whether people smoke or not, and what their biological sex is, we can use any of the three following graphs: the clustered bar graph, the mosaic plot, or the stacked bar graph. We're going to identify each of the graphs below, and we're going to write down what the R code will be for each of these, and then we're going to include a description of the data based on all of the graphs together. So the first graph you see is smokers by sex, and I have sex on the x-axis, and then notice I have a legend. This legend is whether they smoke yes or no based on color. And if I had done this code in the reverse order in my frequency table, I would have whether they smoke or not on my x-axis, and then biological sex would be in my legend. And that would be completely fine. The graph will tell you the exact same thing. This graph has all of the females' answers in one bar, one color on top of the other. So this is called a stacked bar graph. You guys, there are certainly times to use a stacked bar graph. I don't particularly like it because you have to work pretty hard to see the difference in the gray sections because they don't start at the same spot. And so I don't particularly like stacked bar graphs. They're nice for showing overall totals, but that's about it. And then the code for doing a stacked bar graph is bar plot of your frequency table. And our frequency table up here is smoking table. And so that's what we want to use down here in the bar plot command. So we use smoking underscore table. And so again, that just came from the contingency table we made above. All right, let me write that down. This is the contingency table we make in R. All right, the next graph is a double bar graph. So it has two bars for each biological sex. We could also have smoking on the x-axis, and then our legend would have males and females instead of yeses and nos. So again, we can flip-flop the variables just like we could with the stacked bar graph. This graph is called a clustered bar graph. It's also sometimes called a side by side bar graph. That's not typically what it's called when there's more than two bars, but if there's more than two bars, people typically call it a clustered bar graph. The R code for this particular graph is a bar plot, again, of our contingency table or our frequency table. So we have to do smoking underscore table. But this time, if I just close that parentheses there, I would get a stacked bar graph. So I want to unstack it. So I have to include beside equals true. And our contingency table is here. It's the smoking table. And then we add the command beside equals true. And then finally, the last graph that we have is called a mosaic plot. I don't particularly like mosaic plots, but they are heavily used in biological sciences and in the social sciences. So it is something many of you will see. So in a mosaic plot, you rarely have X and Y axes. And so instead, you're relying solely on the area you see with your eyeballs. It has one variable on one side and the other variable on the other axis. And then it'll tell you male, female, yes, and no on each of the columns or rows. And your eyeball has to look at the area to see any differences or things you need to explain. The code for a mosaic plot is exactly that. It's mosaic plot, parentheses of our frequency table again, or our contingency table again, which is smoking underscore table. Okay, so now let's look at these graphs and see what we can learn from them. So when I look at all three of these graphs, I see that it looks like there are more males than females in all of these graphs because there's more area for all of those. And it also looks like, particularly with this side-by-side or clustered bar graph, that more females smoke overall. And the same thing is true when I look at the mosaic plot. There are more males than females because the green bar is taller. And then there are more females who smoke. And then I can agree that the same thing is true with the stacked plot. So I would make a description of any or all of these. And I would say we can see there are more males than females in the study, but more females smoke. And so that would be our description of the graph. GR. All right, so we would have this description no matter what graph we used. So real quick, why do we use one graph versus the other? You guys, each of them has their benefits and drawbacks. Look at all three graphs really quickly. You don't even have to make them pretty. Just look at them really quickly and see which one best describes what you want to present, and then choose that graph to present and then make it pretty. For your purpose or for the field of study you're in, use whichever one is most reasonable. So before we do this in our studio, we're going to talk about one more thing here. We only have two possible answers for biological sex, and we only had two possible answers for smoking. But you guys, when we have variables like this, it is quite possible there's more than two levels. And here's just an example that you could have. So instead of biological sex, we're looking at gender, and somebody may answer male, female, or other. And then variable two was smoking, and we might have yes, never, occasionally, or yes, but quit. So this would change how many rows and columns are in the contingency table and how many color combinations there are in the graphs. So depending on whether you have variable one or variable two on your x-axis, if you have variable one on your x-axis, you would have three colors. If you had variable two on your x-axis, you would have four colors. So it just depends on which one's on on your x-axis. Actually, I think I reverse those. I think that if it's genders on the x-axis, you have 4 colors. Yep, I've got those backwards. So we'd have 4 colors, and then we'd have 3 colors. It doesn't matter. R is going to make it for you. But the point is, it just adds another color every time there's a new level. All right, so now we're going to do this in our studio, and you guys are going to see the code in the video. You're going to have to fill it in.